Hello class, this is our first video on the topic of kinetics, which discusses the rate of reactions. So chemical reaction rates. In a chemical equilibrium, the forward and reverse reactions occur at equal rates. The rate of the reaction is the change in the amount of a reactant or product per unit time. So this does not have to do with whether or not we have more products or more reactants, which has to do with the K equilibria, which we've been discussing, but this is a rate of how things change over time. So if we consider the reaction from A to B, the concentration of A is going to be decreasing, and we can discuss that in terms of a rate of negative delta A concentration over delta T. So what that means is that we have the concentration of A is changing over time as time changes. And the concentration of B, our product, is therefore going to be increasing. So delta B is going to be increasing. So we have a positive delta B over delta T. So let's look at one example of how data can be used to figure out the rate of a reaction. So in example 1, we're discussing the rate of decomposition of hydrogen peroxide. So if we have two equivalents of hydrogen peroxide, that reacts to form two equivalents of liquid water and oxygen gas. And here we have a set of data in this table where time is increasing by 6 hours. So we have time 0, 6 hours, 12 hours, 18 hours, and 24 hours. If we fill in our table, what we can see is that the concentration of hydrogen peroxide is decreasing from 1 molar to 0.5 molar after 6 hours, to 0.25 over 6 hours, to 0.125 over the next 6 hours, and so forth. We can then look at how our concentration of hydrogen peroxide is changing. That's what this delta means. So it means that it's changing. So from 1 to 0.5, it's decreased by half. And then from 0.5 to 0.25, it's decreased by 0.25. And then from 0.25 to 0.125, it's decreased by 0.125 molar. And then we can compare that change in concentration to our change in time. And as I said, each of these intervals is 6 hours apart, so our delta T in hours for each of these is 6, 6, 6, 6. So what is our rate? Well, the rate is actually changing as time progresses. So in the first interval, we have a change in molarity over time of negative 0.0833. And then our second interval is negative 0.0417. And then 0.0208, and then negative 0.0105. So our rate is actually changing. So there are a few different definitions that we need to consider when looking at a table like this. First, this data point here is the average rate over the first 6 hours. This data point here is the average rate over the second 6 hours. So as 6 hours pass, the concentration changes over time, and that rate is changing. So it's actually decreasing. So if it were sort of sloping down. So let's take a look at how to calculate this. So the rate of decomposition from time 0 to time 6 for H2O2 decomposition is going to be equal to the delta H2O2 concentration over delta T. And so we take our final time minus our initial time. So this, in this example, is going to be time 6 over time 0. So our H2O2 concentration at time 6 minus time 0 is going to be divided by our time at 6 divided by our time at 0, which is going to be 0.5 minus 1 over 6 minus 0, which is negative 0.5 molar over 6 hours, which ends up being negative 0.0833 molar per hour. So let's define a few things. First, the average rate is the rate over a time period. So this is your concentration at final minus initial divided by time over time final minus time initial. The instantaneous reaction rate is the rate at a specific time, as small of a delta T as you can get. Now if we scroll back up, we can look at each of these intervals as being 6 hours. That is certainly not an instantaneous rate. That is a very long period of time, which is why we would consider this an average rate over a long period of time. An instantaneous rate would be measured over the order of a few seconds. The initial reaction rate is the instantaneous rate where time equals 0. This is the smallest interval you can possibly get where time initial is equal to 0. Now let's take a look at, once we know the reaction rate of something, we can use stoichiometric ratios to figure out different components of the reaction. So for example, once we know the reaction rate of, say, N2 or NH3 once we know the reaction rate of NH3 decomposition, we can then calculate the N2 formation relative to that. So let's take a look at how we use stoichiometric ratios to determine such a thing. So we have two equivalents of ammonia react to form one equivalent of dinitrogen gas and three equivalents of dihydrogen gas. So if the rate of decomposition of ammonia is compared to the rate of formation of dinitrogen, well, we can say that the decomposition of ammonia over time times 1/2 would be equal to the rate of formation of dinitrogen over time. Where does this 1/2 come from? It comes from the molar ratio, where if we have ammonia times a certain value of x, it's got to be equal to dinitrogen, and that x has got to be 0.5 because you have twice the amount of ammonia versus dinitrogen. So the stoichiometric ratio for dinitrogen over ammonia is 1/2. So if we have the rate of decomposition of ammonia and we multiply that by 1/2, we would get the rate of formation of dinitrogen. Let's see an example where we use that information. So in example 3, at time equals 500 seconds, what is the rate of H2 formation if NH3 decomposition is 1.94 times 10 to the negative 6 molar per second? Well, our rate of decomposition of ammonia over time is here, negative change in concentration over change in time, which is going to be equal to 1.94 times 10 to the negative 6 molar per second. Our stoichiometric ratios for hydrogen formation versus ammonia decomposition is going to be equal to 3/2 the decomposition of ammonia. And that's due to the 3/2 molar, 3/2, of hydrogen gas versus ammonia. So if we take that rate of decomposition, negative 1.94 times 10 to the negative 6 times 3/2, we would get the rate of formation of hydrogen gas over time, which is going to be equal to 2.85 times 10 to the negative 6 molar per time. So let's talk a little bit more about reaction rates and factors in a reaction that affect the rates. There are 4 factors that can affect the reaction rate: concentration of the reactants, temperature, a catalyst, and the surface area. So catalyst and surface area are interrelated to one another, especially if you have a catalyst that's heterogeneous, one that's not in solution. The catalyst lowers the activation energy to get to a product, but that is going to be for a different time. What we're going to be focusing on is the concentration of reactants and temperature. So how do these two factors affect the reaction rate? It is proportionate to collision frequency. So in order for things to react sometimes, the molecules that are literally in the flask need to interact with one another. And rate is proportional to collision frequency. So as you increase the concentration, you have more interactions, you have more collision frequency, and you have a faster rate. If you increase temperature, you end up with more kinetic energy. And so your molecules are moving around faster. That would also increase your reaction rate. Next, we're going to look at rate laws, arguably the most important part about the kinetics unit. Rate laws come from experimental data, and they are mathematical expressions that describe the relationship between the rate of a chemical reaction and the concentration of its reactants. So in a moment, what we'll do is we'll cover rate laws, and then we'll go back and see how the stoichiometric ratios kind of factor into that. So rate laws are derived from experimental data always. It is not possible to look at a general reaction, such as A and B reacting to form C and D, and derive the rate law. You must have experimental data. So let's see how this works. So for a general reaction, we have A reacts with B to form C and D. If we were using our K equilibrium constant, the products raised to their coefficients would be divided by our concentration of our reactants raised to their coefficients. Now, for our rate law, how quickly things are reacting with one another, that is going to be equal to K, our rate constant, times the concentration of reactant A raised to the exponent m, times concentration of B raised to the exponent n. It is really important to note that m and n are not the coefficients of, are not exponents that are coefficients. Coefficient exponents show up in equilibria constants only. So our rate is equal to k times a raised to m times b raised to n. K is our rate constant, k is temperature dependent. K is not an equilibrium constant. So I'm going to draw it with a little swoop to make it a little fancy and indicate that it is not an equilibrium constant. So what are m and n? They define how the rate is affected by reactants. It is dependent on the rate-limiting step of the reaction. So some reactions take place in multiple steps. The slowest step is going to determine the rate law and the rate of the reaction, always determined experimentally. The order describes what is happening at the rate-limiting step, and it is dependent on the exponents. For example, a first-order reaction, which is common for decomposition, the rate law might look like this. The rate is equal to k times H2O2 raised to the power of 1. That's going to be the only time that I actually write the 1. If there's no number there, it is implied that it is a 1. M is equal to 1 there. The sum of our exponents is equal to 1. That is a first-order reaction. A second-order reaction is common when things collide. So here's an example where we have rate is equal to k, rate constant, times the concentration of C4H6 squared, indicating that even though we have one type of thing, it must collide with itself in order to react. M is equal to 2, which is our exponent. The sum of our exponents is 2, indicating that it is a second-order reaction. There is another way that we can get a second-order reaction. For example, when the rate is equal to k times a proton times water, so this is a situation where water and proton might be reacting to form hydronium. Both of those exponents are an implied 1, so we have m and n both equal to 1. Our sum of our exponents is also 2. So these are both situations of a second-order reaction. What we're going to do now is take a look at how to determine the order of the reaction. So for example, for the reaction below, the rate is determined to be rate is equal to k times NO squared times H2. And here's that reaction. What is the order with respect to each reactant and the overall reaction? Well, the NO is a second order, which is 2. H2 is a first order, an implied 1. The overall order of the reaction is 3, a sum of 2 and 1. It is considered a third-order reaction. Third-order reactions are very uncommon, but they do happen occasionally. So let's see where we get this information from. And I should note that the fact that the NO coefficient 2 and the coefficient 1 is a coincidence. These values must be determined experimentally. So let's take a look at example 5. This is a reaction that takes place in our upper atmosphere as the ozone layer is depleted by reacting with nitric oxide, which is a greenhouse gas. So nitric oxide reacts with O3 to form NO2 and O2. Now, what's presented here is a table of trials which include changing the concentration of the components and observing the rate of one of the components. So let me say that again. What is shown here in this table, in each trial, each row, is manually altered concentrations of our reactants and observing how one component of the reaction changes over time. So what's happening here is in 4 different trials, the nitric oxide concentration has been changed, the ozone concentration has been changed, and NO2 concentration, the formation of it, has been observed. And we can use this set of data to determine the order of the reaction. So for example, when we are determining the coefficient m, which is the coefficient, the exponent m, which is going to be the order of NO in this reaction, we must keep ozone constant. So, for example, in trial 3 to 4 in pink, NO varies, that was done on purpose, while ozone was kept constant. In those reaction situations, the formation of NO2 over time was observed to change. How much did it change? Will tell us the order for NO concentration. So, trials 3 to 4, ozone is kept constant while NO changes. The value for m, our exponent, is going to be equal to the change in NO concentration over the change in rate. So, as the concentration of NO goes from trial 3 to trial 4, you take 4 divided by trial 3, and we get 2. So that's 2 times 10 to the negative 6 divided by 1 times 10 to the negative 6 is equal to 2. and then we see how the rate changes. So the rate of trial 4 is 3.96 times 10 to the negative 4, divided by the rate at trial 3, which is 1.98 times 10 to the negative 4. We divide those numbers and we get 2. So then we take the change of NO over the change in rate, and we get 2 over 2, which equals 1. So our m exponent for NO is equal to 1. Now we're going to do the same thing for ozone. In order to determine how ozone changes, or how ozone affects the rate, NO must be kept constant. So from trial 1 to trial 2, when the experiment was performed, NO was kept constant, ozone was changed, it doubled, and the effect that had on the rate of formation of NO2 was observed. So let's see what happens. So we take NO, we hold it constant. The change in ozone from trial 2 to trial 1, we divide those. 6 times 10 to the negative 6 divided by 3 times 10 to the negative 6 is equal to 2. The change in rate was 1.32 times 10 to the negative 4, which is a larger number, divided by 6.60 times 10 to the negative 5th, which is a smaller number that is also equal to 2. So n, our exponent, is going to be the change of concentration over the change in rate, which is equal to 2 over 2, which is 1. So what does this mean for both of these? This means that when you hold ozone constant and you double the NO concentration, the reaction rate of NO2 doubles. When you hold NO constant and you double the concentration of ozone, the reaction rate doubles. So there's a direct relationship between the rate of formation of NO to the concentration of ozone, and there's a direct relationship between the formation of NO to, of NO2 over time versus the concentration of NO. So both of these two reactants affect the reaction rate of this reaction. We can now write the rate law. Our rate law is going to be equal to K times the concentration of NO raised to the power of M times ozone raised to the power of N. We have just calculated that M and N are both equal to 1, so this is our rate law for this reaction, and it is a second-order reaction. We now need to calculate the value of our rate constant, and we can use any trial for that information. What we're going to do is use trial 2, where we take the concentration of NO raised to its exponent times the concentration of ozone raised to its exponent. So, and we plug that in and set it equal to the rate. And we solve for K. So our rate for trial 2 is 1.32 times 10 to the negative 4th. That's going to be equal to K times the concentration of NO for trial 2, which is 1 times 10 to the negative 6, raised to its exponent, which is 1, times the concentration of ozone for trial 2, which is 6 times 10 to the negative 6, raised to its exponent, which is also 1. 1.32 times 10 to the negative 4th is going to be equal to K times 6 times 10 to the negative 12, and we calculate for K, and we get 2.20 times 10 to the 7th. So that is how we use experimental data to solve for the reaction rate law, rather, and then we can use any trial to solve for K, our rate constant.